Hi, this is Charles Schaefer with CDM Smith, and this is the audio file for a final summary report for our CERTA project ER 2424 entitled Investigating Electrochemical and Reductive Treatment Approaches for Perfluoroalkyl Contaminants in Groundwater. The project team for this project includes CDM Smith, Aptum, Colorado School of Mines, University of Cantabria in Spain, and also Duke University. The overall goal for this project was to develop and assess the use of electrocatalytic and UV reductive approaches for treatment of PFASs in groundwater. Now, when we started out, we actually were initially looking at some catalytic reductive approaches. We soon found out that this was not going to be, at least with the catalysts we were looking at, the best path forward for the perfluoroalkyl acids. So then we began looking at these UV reductive approaches using sulfite. This work was primarily done by Tim Strothman's group at the Colorado School of Mines. For this presentation, we're going to focus on the oxidative electrochemical or electrocatalytic approaches. And in this work, we intended to, and we measured degradation rates. We wanted to identify PFAS transformation products. And again, not just looking at target compounds, but also a lot of the suspect analytes for which these libraries have been developed. We wanted to evaluate the impacts of co-contaminants in geochemical conditions we looked at both simple electrolytes and natural groundwaters. We wanted to look at treatment, again, for a wide range of PFAS, which includes a lot of precursor compounds, and also evaluate the potential for long-term treatment. So what I'd like to talk about is some of the experiments we did with AFFF impacted groundwaters. We're going to skip some of the initial work we did with our anode screening and also some of the work we did in simple electrolytes. But what I have shown here is just a setup for the electrochemical experiments. You can see the electrochemical cells that we used, and they were commercially available cells. We had them set up in duplicate here so we could run 2 at a time. So you see the electrochemical cells, and we ran them in a batch mode where we would recirculate using a peristaltic pump about 250 mils of our AFFF impacted water through the parallel plate electrochemical cell. Typically, we used a current density of about 25 milliamps per centimeter squared, but we did several experiments at either a slightly higher or lower current densities. The reaction time was typically about 8 hours. Again, the anodes that we used were from Condius. They were a boron doped diamond on niobium. We used a stainless steel cathode, and there was about 4 millimeters of spacing. The 2 types of groundwater we used a natural groundwater, which was collected from actually a DoD facility from a non-AFFF impacted area. We just wanted a good natural groundwater. And then we had some 3M AFFF that we used to spike this groundwater. Then we also got some AFFF impacted groundwater from a former fire training area at Ellsworth Air Force Base. For the experiments, we typically did a lot of analyses, both at Duke and at Colorado School of Mines, including LC-MS-MS and high-res mass spec. We did a lot of work to evaluate the fluorine mass balance, and then we also did a set of experiments for longer term, where we ran in 24-hour batches and did a new batch for about for over several weeks. So these were the basic nature of the experiments that we performed. Shown in this slide are just some of the groundwater geochemical parameters for the 2 types of groundwaters that we used. Yeah, nothing, I guess, incredibly exciting jumps out here, but there is, I think, one significant difference, and that's in the hardness. You have around 360 milligrams per liter of calcium hardness in the first groundwater, but in the Ellsworth you have slightly over 1,000, which means there's a lot of calcium hardness there, and we'll talk a little bit how that played out. in our longer term experiments. I guess the other thing to point out is that there is plenty of chloride in both of these groundwaters. And one thing I want to make really clear here is we don't go into it in too much detail in this presentation, but when you're doing any prolonged treatment using boron doped diamond anodes, and certainly that's what you need to defluorinate PFAS, you are going to transform your chloride into perchlorate almost stoichiometrically. So that is one potential challenge, not one that you can't overcome, but certainly something that needs to be considered with this technology. Shown in this slide are just the PFAA, perfluoroalkyl acid concentrations in the two waters, and you can see and these concentrations are in micrograms per liter. You can see these concentrations are pretty high, especially the PFOS levels in the first the groundwater that we spiked with 3M AFFF. So at these kind of perfluoroalkyl acid levels, since they're nice and high, it also allows us to see and monitor fluoride generation. We did also look at a lot of the precursors and polyfluorinated compounds, and we'll have a slide a little bit later on that shows some of that. So here are the polyfluorinated compounds and potential PFAA precursors that are in each of these two waters. And these are only semi-quantitative. So how we plotted them is we took their area counts and multiplied them by the fluorine per molecule. Again, we at least can get some sort of semi-quantitative comparison between the levels of these compounds in these two waters. And you can see on the bottom some of the representative structures that are there. So you can see just by the structures how these could at least potentially form some of the perfluoroalkyl acids. And I think the other thing I want to point out is in the Ellsworth Air Force Base groundwater, you have about 5 times the number, or at least based on an area count, of these compounds present than the 3M AFFF. So one might think by looking at this is that the Ellsworth Air Force Base groundwater would, upon oxidation, maybe generate more of these perfluoroalkyl acids. So we're going to look at this and see, and knowing that this is the polyfluorinated compounds that we see in each of these two waters, we're going to see what happens when they undergo electrochemical treatment. So first, considering the groundwater that we spiked with 3M AFFF, and again, this is a natural groundwater spiked with AFFF, we looked during this 8-hour experiment at some of these polyfluorinated compounds that were initially present in the diluted AFFF, and we can see on the left here that generally these compounds were rapidly removed, and I just showed some of the more abundant compounds based on area that were present there. What was also interesting is we actually saw some transient increases of compounds that were either non-detect or maybe at the only very trace levels, but they clearly showed an intermediate increase and transient increase during electrochemical treatment, and then they started to go away again. So we saw that we were forming some compounds and also removing these compounds, and this gave us at least some initial insight into the oxidation pathway and also potential formation of perfluoroalkyl acids. So here are some results with respect to the perfluoroalkyl acids during our 8-hour experiment. And again, for this, we took initial measurements of PFAS, then at 3.5 hours, and then at 8 hours, basically at the end of the experiment. And what we can see is, what we have shown here is on the top left, we have the perfluorinated carboxylates, and in the bottom left-hand corner, we have the perfluorinated sulfonates. Now we'll start in the bottom left-hand corner here. You can see that the breakdown of compounds, but you can see over time, the perfluorinated sulfonates, they all decrease over time, and not just the long chain compounds, but you see these decreases in the short chain compounds as well. You don't see any indication of any sort of transient intermediates forming or any transient generation of the perfluorinated sulfonates. So I think this is a pretty nice story here. And again, we see both the long and the short chain compounds going away. But we have a different story for the perfluorinated carboxylates up in the left-hand corner. What we see really clearly is at 3.5 hours, we see a very large transient increase of these compounds. In fact, at 3.5 hours, it's about 3 times what they were at time zero. But then they start to decrease. Now, they haven't decreased below their initial concentrations, but if you look carefully at the size of each of the bars for each of those compounds, they're all getting smaller. So again, we're seeing these compounds start to decrease. And why we think we see this intermediate increase is because of all those polyfluorinated compounds that you saw for the 3M-AFFF. Now again, it wasn't as much as the Ellsworth water, but certainly we know these compounds were there. They went away. We saw these transient oxidation intermediates on the previous slide. So we think that this transient formation is due to oxidation of precursors. Well, to kind of confirm this, we took some of the untreated 3M-AFFF spiked groundwater here, and we did a total oxidizable precursor assay on it. And not unexpectedly, what we saw from this is we really didn't see any increases in the perfluorinated sulfonates, but we saw pretty substantial increases in the perfluorinated carboxylates, and again, pretty analogous in terms of the extent to what we're seeing here. So this was a good confirmation that the top assay, the total oxidizable precursor assay, was a pretty good indicator of what we would see going on electrochemically, both in terms of the perfluorinated carboxylates, and it was also very consistent in that both the top assay and our electrochemical treatment, as well as, and again in the previous couple of slides where we showed all based on our libraries, all of these polyfluorinated compounds that were present. All three of these types of tests and approaches showed a very consistent story, that we had a lot of these polyfluorinated compounds present, that they had structures that it looked like they could form, in this case perfluorinated carboxylates, and that's what we got here. So this was a very satisfying findings. So kind of putting these results for this 3M-AFFF spiked groundwater together, we developed a oxidation pathway starting with some of these most abundant precursors that we found. And and basically all the intermediates that you see here, they were compounds that we were able to identify as transients through our high-res mass spec analysis of these electrochemically treated waters. So we can see that initially some of these precursors go through these various oxidation steps, which can be dealkylation, oxidation of terminal amines, eventually forming these sulfonamides. You get some nitrogen removal there. You actually form sulfinates, and then you get further oxidation of that, and then you form your perfluorinated carboxylic acids. And based on some of the results that we've seen in some of our early studies, as well as a lot of results shown by others who's looked at electrochemical oxidation, you get this unzipping of the perfluorinated chain, and you get release of fluoride here. And we did see measurable fluoride generation here. So again, this pathway seemed pretty consistent and seemed reasonably well understood. So now we get to the results for the Ellsworth groundwater. And again, this was collected from water in a fire training area where AFFF has been used. And results are a lot different here. We do see a lot of these parent polyfluorinated compounds go away, but we really don't see any, or at least not very much, transient precursor generation there. At least nothing compared to what we saw in the previous water. And this is a little surprising, because remember, there were about 5 times, again based on area counts, 5 times the amount or the concentration of polyfluorinated compounds in this water compared to the 3M AFFF spiked water. And then we look at the perfluoroalkyl acids, and again we have the perfluorinated carboxylates in the upper left and the perfluorinated sulfonates in the lower left-hand corner. And what we see for both sets of compounds here is we see them both decreasing over time. And while this is, about the same as what we saw for the perfluorinated sulfonates before, so no major difference there. Again, we see both the large and the short chain perfluorinated sulfonates decreasing over time, which is good. But we essentially see the same thing for the perfluorinated carboxylates. We don't see this transient increase in perfluorinated carboxylates here. Now, initially we thought, well, maybe the kinetics are different here, and maybe we just missed it. So we did some additional tests and we monitored it at some shorter times, but there was no transient increase of the perfluorinated carboxylates, which suggests that those polyfluorinated compounds that were there that we know got removed, and they got removed very quickly within the first couple hours, weren't ultimately forming these perfluoroalkyl acids, neither the carboxylates nor the sulfonates. And again, this is a little surprising given there was about 5 times the number now of these polyfluorinated compounds. Now again, the compounds were slightly different. They weren't exactly the same, but they were similar enough to where we thought we would see this. So we saw none of these or very little of these intermediates formed. We saw no perfluoroalkyl acids, despite the fact that there was so much more of these polyfluorinated compounds in this Ellsworth water. So we again did perform the top assay on this water. Again, this was just the raw prior to electrochemical treated Ellsworth water. We did the top assay, and sure enough, the top assay, consistent with the results shown here, did not show any formation of perfluoroalkyl acids, neither the perfluorinated carboxylates nor the perfluorinated sulfonates, as a result of the top assay. So this is pretty interesting, and seems to all this information seems to contradict the results we got from the high-res mass spec analysis, which says there was basically a lot more polyfluorinated compounds in the Ellsworth groundwater. Basically, that the top assay, looking at intermediates, and the data shown here on the perfluoroalkyl acids would suggest that there really aren't any polyfluorinated compounds, or at least anything of note here that we would expect to see these products. But yet we know those polyfluorinated compounds were there. So what's going on, and what does this mean for evaluating treatment? How do we evaluate the PFAS and the fluorine mass balances here? So what we did here was take a little closer look at our fluorine and fluoride mass balance. So as I mentioned, we were doing a fluoride analysis here just to verify that we were generating fluoride, the concentrations were high enough. And what we did is we looked at our total fluorine, and this is the blue bars here, either as fluoride, and then also the fluorine that was in the perfluoroalkyl acids. So this is our time zero, our initial or untreated water. Then you can see at 3.5 and 8 hours, you can see that total number goes up. So you have a couple of things happening here to cause that, right? So you definitely see as you remove the PFAS, that's generating fluoride, and that's why you see the shift more from the open to the filled bars. But you also see this total number going up, right? So something else has to be contributing to the PFAS and/or fluoride here, and we hypothesize that it's the fluorides, because you didn't see any increase in PFAS. So that must be coming from these polyfluorinated compounds. And in fact, only about a third of the fluoride that's actually generated, if you do the mass balance based on how many perfluoroalkyl acids were initially there, only about a third of that fluoride could have come from that. So about 2/3 of the fluoride that we generated over this 8-hour experiment had to come from these polyfluorinated compounds. So what we did, and Leo Young and his group was nice enough to perform some combustion ion chromatography analysis for us to determine the total fluorine of including both fluoride and total organic fluorine of the raw water, and that's what's shown in this red bar here. And what's really finally very satisfying about that is you look at that total number. Well, that that's about exactly what we were getting and we were seeing at the end of our experiments, when basically we didn't see any polyfluorinated compounds there, and just a little bit of perfluoroalkyl acids left, and a lot of fluoride. So this seemed to kind of tell us mass balance wise what was going on, and I think really highlights the potential usefulness of this tool, both for electrochemical treatment, but I would guess that this might be very important for a lot of these destructive technologies that are kind of being evaluated and tested now. I think another really important thing is, I think this really highlights maybe perhaps some of the limitations of a TAP analysis, or even just of the top assay, or really just relying on kind of your standard PFAS analysis that most commercial labs can do, which I think now is somewhere in the range of 24 to 30 compounds. I mean, if you just relied on top analysis or standard PFAS analysis, you're not capturing almost two-thirds of the organic fluorine that's present there, and that can be really important when you're trying to evaluate treatment. And I would guess that this could be important in a lot of fate and transport situations as well. So just to highlight some of the key points from some of the things I talked about with electrochemical treatment, I think electrochemical treatment using boron doped diamond anodes remains a promising technology for PFAS, and we're aware that there's other anodes being developed, and certainly they might show some good promise as well. But I think based on what we saw, I think that the fact that these precursor compounds can get treated as well as the perfluoroalkyl acids, we can get defluorination. I think this just continues to show that it's a promising technology. Um, Perchlorate is clearly generated as a byproduct here. We didn't show it in these results, but we were able to show that the electrochemically generated perchlorate, you add some nutrients and electron donor, and it gets reduced. That perchlorate reduces back to chloride. So that, in terms of thinking a treatment train approach, that I think that holds a lot of promise, and that's really a very low cost, low energy treatment to deal with that perchlorate. So while I think it's something that needs to be considered, I don't think it definitely it has that much of an adverse impact in terms of overall cost and treatment that it would rule out electrochemical for being a viable PFAS treatment technology. I think the other very important thing here that we found is that the top assay may not be a good indicator of the polyfluorinated compounds that are present in water. The Ellsworth Air Force Base, the top assay, basically, if we were relying on that to tell you if there were polyfluorinated compounds present, that would have said no, and would have ignored about 60% or 65% of the organic fluorine that was present. Combustion IC really for this water proved to be a much better indicator of the presence of these polyfluorinated compounds, which was consistent with what we saw based on our analytical libraries of these non-target or suspect analytes, and certainly of the fluoride that was generated during electrochemical treatment. So I think if we want to be serious about really evaluating a fluorine mass balance, relying on the top assay alone, at least in its current form, may not be the best approach. So I didn't talk about the UV sulfite work here, but I will say that, and there is a paper in review now for this, that experiments we did with just single solute, single perfluoroalkyl acids, you basically showed the same sort of treatment rates and treatment kinetics that we saw when there was a mixture of these compounds, either in AFFF impacted groundwater or using diluted AFFF solutions. And again, with respect to this UV sulfite treatment, site-specific geochemistry can really alter reactivity kinetics and rates, and needs to be considered in treatment design. And that's the conclusion of this presentation. Thank you.